Welcome to the first Capacity Building Event 2022 on the Food Contact Materials International Regulatory Framework and Food Contact Materials Recycling Regulations and Guidance. This event is organized by the Global Food Regulatory Science Society, G-Force.
Esteemed colleagues, ladies and gentlemen, welcome to this second day of the capacity building events organized by the Global Food Regulatory Science Society and dedicated to food contact materials. We will continue our discussions about food contact material, their assessment and their regulatory management. And we will be devoting today's discussions to recycled materials with emphasis on plastic materials and recycled plastics in particular. This event is brought to you by the Global Food Regulatory Science Society in partnership with the International Union of Food Science and Technology, in partnership with the Dubai municipality, and with the Food Risk Analysis and Regulatory Excellence platform of Université Laval and of the Institute of Nutrition and Functional Foods. My name is Samuel Godefroy, and I'm a professor of food risk analysis and regulatory policies at Université Laval, and I have the privilege to serve as president and chief executive officer of the Global Food Regulatory Science Society. If you allow me, before starting this event, and for those of you who are joining us for the first time, I would like to introduce the Global Food Regulatory Science Society in a few words. We are a non-for-profit organization that was created in 2019 and incorporated in 2020 in Canada. Our main objective is to promote food regulatory science, to promote knowledge development, knowledge dissemination and sharing, but also the development of capacities and competencies in food regulatory science. You're going to ask, what are food regulatory science? They are all the scientific disciplines that intervene and that underpin food regulatory decisions. We have the privilege also to be a disciplinary organization of the International Union of Food Science and Technology and to contribute to the overall field of food science. Now, as part of our mandate and our mission to disseminate knowledge related to food regulatory science, we have developed a series of events, of capacity building events related to different aspects of food regulatory science, to risk assessment, regulatory policies, food laboratory science, the various fields essentially that support making those regulatory decisions. And we have started these events this week with the first event dedicated to food contact material. We had the privilege to be with you on the 22nd of February from Dubai with a number of experts from various parts of the world, from Canada, from Australia and New Zealand, from France. And we had the opportunity to introduce food contact material and aspects related to their assessment, as well as their regulatory management in various jurisdictions. Today, we will continue the discussion about recycled materials. But prior to doing that, if you allow me, I would like to introduce my colleague, Dr. Amin Assouf, who is a research scientist in the Global Food Regulatory Science Society, and will offer us a summary of what was discussed in the first day prior to starting the discussion about recycled material. So Amin, the floor is yours.
Hello, everyone. Thank you, Professor Samuel, for the introduction. I hope everyone is enjoying, they are enjoying their time with us during these selection of webinars targeting food contact materials. So for the first day, our webinar dealt with the Food Contact Materials International Regulatory Framework. So we had 4 speakers, 4 presentations for the first day. We were honored to welcome first Professor Sandra Domenech from AgroParisTech, myself also for a presentation, Dr. Mark Feely from Canada, and Dr. Scott Crerar from Australia and New Zealand. So the first presentation given by Professor Sandra Domenech was entitled Introduction to Food Contact Materials and Their Interactions with Foodstuff. So Dr. Sandra started by stating the frame for our two-day webinar by introducing what are food packaging materials with a focus on plastic food contact materials. Then she introduced the different interactions that can occur between food and packaging material, impacting the quality of food like permeation and sorption, but also and most critically impacting the safety of food as migration. Then Dr. Sandra explained also the different approaches to assess the exposure to hazards migrating from food contact materials, which can be performed through experimental migration tests, but also through migration modeling. And then Dr. Sandra also introduced the problem and the problematic of plastic recycling for reuse as a food contact material. She spoke about the problems, the challenges of the use of recycled plastics, such as the misuse of food contact materials in their previous use, the lack of sorting of wastes or plastic wastes, the problem of cross-contamination, and the efficiency of recycling processes. So Dr. Sandra helped us in order to introduce well our webinar for today. And then we had a presentation, or effectively 3 presentations related to the international regulatory framework of the food contact material problem and topic. So we had 2 presentations given by myself on the European Union framework and on the US FDA framework. And then Dr. Mark Feely presented the approach of Health Canada related to this topic. And then Dr. Scott presented the approach from the point of view of Australia and New Zealand. Effectively, the 3 presentations orbited or around the same structure related to the different food contact materials regulations. So we explained, different speakers explained the general requirements imposed by the different international jurisdictions, as well as the different structures or the general structure of the different legislation, which present normally positive lists of authorized substances with their permitted limits, then the different migration or extraction tests to be performed, and finally, the different approval processes or the declaration of compliance to be performed in order to validate the compliance of a food contact material. Effectively, we had yesterday, or during the first day, on the 22nd, we had the participation of a lot of different participants from different countries. So overall, if we can go to the last slide, please, if you please. So overall, we had a total of 224 participants. We reached a maximum peak of 182 participants connected at the same time. And luckily, we had the participation from 64 different countries. So we had a very broad international audience during the first day. So thank you, and I hope you will enjoy also our webinar for today.
Now, we will continue our discussions about food contact materials, and we will be discussing today an important area, considering, in fact, the emphasis on the sustainability agenda, considering the emphasis on the need to save energy and to protect the climate. The possibility of using recycled materials in various applications, including food contact application, is really being looked at by a number of jurisdictions around the world. Industry has developed various applications in this regard, and also enabled, in fact, the possibility of making available these materials for use in food contact applications. Regulators need, of course, to accompany this effort by providing the guidance that is needed to understand the suitability of the materials, the suitability of the processes that are used to develop these recycled materials, and to allow their possible utilization for food contact applications, including food packaging material. This is going to be the topic of our discussions today. We will start, first of all, by discussing aspects related to the assessment of recycled materials and recycled plastics. And the first presentation comes to us from Canada, from Dr. Mark Feely. Mark is the former Associate Director of the Bureau of Chemical Safety in the Food Directorate at Health Canada, a senior food toxicologist and a food chemical safety expert. And Mark will offer us a presentation related to assessment of these recycled material. So Mark, thank you for being with us today, and the floor is yours.
Hello, Samuel and everybody. I take it you can hear me, okay? Hello. So everybody can hear me all right?
Yes, we can hear you.
Okay, thank you. First of all, I'd like to thank Professor Godfroy and the Global Food Regulatory Science Society for allowing me to participate in this very important activity and to provide a general introduction to recycled plastics. I mean, essentially, as Samuel had mentioned, it's sort of a rapidly evolving field, and what I will attempt to do is try to explain, you know, why there's such great attention associated with this area. So I see that my presentation has been queued up. So Amin, are you able to advance through the slides? Okay, so essentially what we'll be attempting to do today is to provide an overall introduction to recycled plastics, what they are. But I think one of the more important aspects is for people to understand what are the main drivers for producing recycled plastics. And then essentially we will end this particular presentation with, you know, what specific considerations involved in the risk assessment process are required for recycled plastics, and this is specific to food packaging, because there are recycled plastics used for cosmetics, therapeutic products, etc., non-food items, but what we'll be focusing on is specifically recycled plastics that are currently in use for food packaging material. So next slide. So essentially, you know, why is there a continued or increased interest in recycled plastics? And I've put together some of the issues specific to North America, but these are likely relevant for the rest of the world. So essentially, what we're seeing is that there is an exponential increase in the use of plastics as material for all sorts of packaging, including food packaging. And the latest estimate as of 2014 was that there was over 300 million tons of plastic that had been produced. Now, the major issue that we see is the fact that the vast majority of this plastic that has been produced escapes any attempt at recycling. And this is specific to plastics because essentially there's an attempt to only collect approximately 14% of packaging used for food plastics for recycling, with the rest either going to landfill, waste incineration, or just escaping the collection system. In comparison, when we look at paper and steel or other metals that are used in food packaging, the typical recycling of these materials is up to 90%. So essentially, it has identified the unique properties of plastics that make them somewhat difficult to recycle. I think probably the major issue that is currently topical and resulting in the majority of nations taking a harder or strong look at recycling plastics is the amount of plastic waste material that's ending up in the ocean every year. So essentially what we're looking at is the latest estimates by a publication from the New Plastics Economy indicates that every minute there's approximately a garbage truck of plastics dumped into the ocean. And it's what has been estimated is that currently in the worldwide oceans, there's approximately 150 million tons of plastic in the ocean. And there is limited efforts to try to collect this plastic once it receives into the aquatic environment. What's also quite interesting is that based on some recent estimates, it's suggested that by 2025, so in 3 years, for every 3 tons of fish that is removed from the ocean, there will be an equivalent 1 ton of plastic. And at that current rate of plastic input into the oceans, it's estimated by 2050 that the amount of plastics in the ocean will equal the amount of fish that is being taken out. So I think, especially in my thinking, is that this tends to be the major driver in terms of why we're seeing such a increased renewed interest, especially from a number of international countries, on how to deal with plastic recycling. So next slide. So, and these figures are more in relation to the global situation or the worldwide situation. But once again, it emphasizes that only a very low percentage of plastics that are produced are currently being recycled. And essentially the issue is why. Well, currently, and this situation may change in the near future, one of the reasons for a low rate of recycling is due to the low cost of the monomeric feedstocks that are used to produce plastic polymers, because these are all derived from oil. So essentially the cutoff point is approximately $90 US a barrel. As long as oil is less than $90 US, it's actually cheaper to make plastics from the virgin starting material, which is oil, than to go through a recycling process. The other major issue is that in certain areas of the world, especially North America and particularly Canada, there's sufficient landfill space, so this is an inexpensive dumping area for an amount of waste, including plastics. And then it's sort of a catch-22 approach where the plastic industry is producing materials that are attempting to mimic things such as glass and metal for food packaging, for ensuring the safety and shelf life of food. However, in producing some of these materials, they're also providing a plastic that is very difficult to recycle. So essentially, things like low-density polyethylene and polypropylene, which is in a lot of films and bags, and in particular polystyrene, the chemical makeup of these types of plastic polymers makes them very difficult to recycle. And then these are simply, once again, as of 2015, so updated on a worldwide basis, there are billions of tons of plastic waste. And generally, it's only estimated that only about 10% has been recycled. So next slide. And this just illustrates that, when you look at globally the amount of plastics that's being produced, there's only about 2% that is actually being reused for the same or similar products. So there's only about 2% of the total plastic production that's collected from food plastic packaging use that makes its way back into food packaging. And so one of the things that we won't discuss here is that there's an environmental and actually occupational issue associated with recycling plastics. In the U.S., the EPA, the Environmental Protection Agency, is also interested in plastic recycling, but mainly from the environmental aspects. And they have been collecting issues specific to the U.S. in terms of what happens to plastic waste management. So as of 2018, you see that the bottom portion of this area under the curve indicates that the majority is being landfilled. The next major use of plastic waste management is simply collection for recycled energy, because the starting feedstock for the majority of plastic, including those used in food packaging, is oil-based products. And then only a very minor amount actually makes it into the recycling. So, and this next slide simply just illustrates some of the percentages that we have put together in terms of plastic waste generation. And typically what you see is countries with larger amounts of landfill tend to have higher amounts in the landfill. So in the United States, and this figure for landfilling is actually a bit higher in Canada. It's up to about 86%. You see countries with available landfilling will simply collect plastic and have it as waste, whereas other countries with less available areas will collect more plastic and keep it out of the landfill process. But in general, you find that while these countries can have higher amounts of plastic waste being recycled, they also use a higher amount of plastic waste for incineration purposes. So basically, it's keeping it out of the landfill, but it's not recycling because it goes directly into typically heat generation. One of the major areas of heat generation is for cement factories. So now we can, I think one of the major issues that we're seeing worldwide is that at one point, China was accepting almost 50% of the world's plastic waste. And they were using this both for an energy feedstock, so incineration, but also in driving production of new materials for their own economy. However, in 2018, China enacted an import ban on 24 types of recycled materials, including plastics. And this was primarily from an environmental perspective. So, after approximately 25 years of importing over 100 million tons of plastic, China refused to buy any recycled plastic material from countries unless they could clarify or provide evidence that it was 99.5% pure. So what we find is that a complete drop-off of acceptance of plastic waste by China as of 2018, but then other Southeast Asian nations, particularly Thailand and Indonesia, they start to pick up on the amount of plastic waste they will currently accept, and not included in the Southeast Asian nations, but the Philippines are also increasing their collection of plastic waste. And currently, one of the countries that's involved as a major importer of plastic waste is Turkey. So we can go to the next slide. So when we get into plastics, this is just a brief introduction. The green symbol on the left is essentially the universally recognized recycling symbol. And this was developed in 1970. So some people are confused when they see the 1 to 7 symbols that these represent actually recycling symbols, but they're not. These are simply resin codes that were developed later on in the late 1980s. And this essentially identified the type of resin material that the plastic was being produced for. So it doesn't necessarily mean that the plastic can be recycled, but it provides the first step in collection and sorting of like materials in order to facilitate potential recycling. One of the things that we see is that when you produce a plastic, and this is one of the issues with the industry in trying to produce materials that have very long half-lives and provide good protection for the food, is that the decomposition rates when you landfill these materials is very long. So essentially, under best case conditions, you see that the polyethylene terephthalate, and these are these very lightweight, crinkly water bottles that tend to be recycled. In a landfill, decomposition times under the best conditions are approximately 5 to 10 years. And that's in comparison to something such as a high density polyethylene type of bottle, where the decomposition in landfill under best case scenario tends to be at least 100 years. Some of these materials, when you get into the low density polyethylene, which tends to be films and plastic bags, and the category of other plastics, which is sort of a mishmash, number 7, the environmental decomposition of these materials has been measured in hundreds of years, if at all. There are certain materials that are produced and categorized into category 7 that have not been shown to recycle at all under typical environmental conditions. So this is part of the issue that we're seeing, is that the plastic industry initially was trying to develop materials that were mimicking or were at least as good as more expensive materials such as metal and glass in terms of longevity and providing protection for foods. But in doing so, they resulted in materials that tend to be, in certain cases, difficult to recycle and also have very long decomposition rates in the environment. So as we see, the recycling symbols that you see tend to be simply resin identification codes. So it doesn't mean that they can be recycled. Some can be reused, but not all can be recycled. In the food packaging industry, what we tend to find, it's the resin code number 1 and number 2 that are typically most commonly recycled. So the polyethylene terephthalate, once again, the crinkly water bottles that everybody's used to, they tend to be recycled usually only once and have the highest rate of plastic recycling. And that's simply because there's been a standardized size approach to these type of materials. And the contents of the materials is relatively well characterized. The high density polyethylene, this is a type of plastic that also has a very long half-life. Environmentally, it's very stable. It has good structural integrity. And the high density polyethylene is an example of a packaging material that can be recycled on numerous instances. So what you find is that you get into doubling, tripling, quadrupling, quintupling of the use of these type of HDPE materials before the integrity of the plastic starts to break down. So whereas the PET typically only is recycled once, HDPE can be recycled on numerous occasions. And once again, that leaves that typically the type of plastics found in resin codes 3 to 7 are more difficult and expensive to recycle. So unless there's a particular driver forcing the recycling, they tend to be going into landfill and not part of the local recycling programs that might exist. So essentially, the take-home message for this is that just seeing a plastic recycling code on any product doesn't mean it will be recycled. It simply is a starting point of potential recycling. And this slide is just a graphic illustration. Generally what you find is plastics that are difficult to recycle make up the majority of the plastic waste. And so you see that the low density polyethylene and the polypropylene make up the majority. So things such as plastic wrapping, straws, takeaway cups, bottle caps, plastic bags, and sandwich bags are included in these two types of products. So I guess what's also not illustrated here is that even though you have two categories of plastics, the polyethylene terephthalate and the high density polyethylene, and these are in blue, even though these represent the most common types of plastics that are recycled, they are also responsible for a significant amount of primary plastic waste. And it's also been estimated that in all these plastic waste that gets to landfill, approximately 80%, which ends up in the ocean, is coming from these landfill sites. So it's not deliberate dumping, but it's indirect dumping, and it's coming from landfill. So at this stage, what I will do is provide a brief introduction to the two main types of food plastics that typically are recycled. So the first one is the polyethylene terephthalate, and as you can click for the next slide. So as I mentioned, it's typical to the water and soft drink bottles. It provides somewhat good structural integrity. The temperature has more restrictive regimes because basically things that are in polyethylene terephthalate are not meant to be frozen. So there's a narrower temperature range, which you would expect from drinks and bottled water. And it's good because essentially when it's put into a liquid state, it can be molded almost into anything. And once again, what you find is from a food use perspective, when you take these monomeric ingredients that are starting, such as the ethylene glycol and the terephthalic acid, you get this liquid polyethylene terephthalate, which can be molded or extruded into a number of different bottle shapes. One of the things that makes polyethylene terephthalate on the specific attraction for recycling is the bottle shapes tend to be somewhat consistent. So a polyethylene terephthalate water bottle from one manufacturer can be used in a number of different manufacturing processes. And in fact, polyethylene terephthalate represents one of the first plastics that has had approval for recycling. So there are currently approved processes involved for manufacturing recycled polyethylene terephthalate. So it's, as I've mentioned, it's polyethylene terephthalate is completely recyclable, whether this is into new packaging material types or whether it's using for other things such as polyester fibers. So the one good thing about polyethylene terephthalate is that about 40% of its energy can be recaptured. And this can be done during the recycling process. So from the strict starting material perspective and the ease of handling and the fact that the majority of polyethylene terephthalate tends to be used for restricted applications, it's one of the more recycled plastic materials currently used for foods. So the next slide. Essentially what we're looking at and can advance is the second most recycled plastic, which is high density polyethylene. These tend to be used for more impact resistant processes. So the containers have a higher structural integrity than polyethylene terephthalate, so they can handle higher weights. You tend to find high density polyethylene used in food and beverage containers, but also for a lot of consumer products, such as shampoos and conditioners and cleaning and dishwasher detergent, etc. And the good thing about high density polyethylene is that it has a higher temperature range. So once again, HDPE is manufactured from petroleum products. And because of its higher impact resistance, as we mentioned, HDPE can be recycled more than once before the structural integrity of the polymer starts to break down. So the latest estimate is that HDPE, a container, can be recycled up to 10 times before the quality is being compromised. One of the major drawbacks for high density polyethylene in that even though the amount of HDPE being recycled is currently increasing worldwide, is the fact that if it does get landfill, it has a very long decomposition rate. And that comes with the structural integrity. So that's that dichotomy that we're seeing, in that the packaging industry is being encouraged to develop products that have very high impact resistance and have a good structural integrity, but in doing so, they increase the environmental half-life. So next slide. So essentially, why do we recycle plastics? Well, I think the major issue, as I've mentioned, is that at one point, the sort of the tipping point for the cost effectiveness shifts to recycling plastics when oil is greater than $90 a barrel, which currently I think it recently passed that, at least in North America. So not only does it conserve limited natural resources, but more importantly, it saves energy. But I think the major driver, which we're seeing internationally, is that it reduces the amount of plastics that can be landfilled. And by doing that, it reduces the amount of plastics that escape the landfill site and end up in aquatic environments, primarily the ocean. So once again, we have an estimate that up to 8 million tons of plastic waste, and this isn't all from food packaging, but a percentage of it is, will enter the Earth's oceans every year. There's also an increased support for the use of plastics, recycled plastics, among consumers. So there'll be a consumer interest outside of that being generated by governments to increase the use of recycling plastics. And I think one of the issues that a lot of the regulatory agencies are currently dealing with is that there's currently undefined human health risks associated with the micro and nanoplastics. And these, once plastics make it into either the environment from the terrestrial or the aquatic, you get entire or continued weathering of these plastics. So they start to break down. They don't decompose into their starting materials, but they become smaller and smaller pieces of plastic. And there's evidence to show that these pieces of plastics are making it into the food chain. The current estimate is that humans, through their average diet, and this is water and food, are probably ingesting about up to 5 grams of plastic per week. So if you consider that, it's about the size of a typical credit or debit card. That's how much plastic the average human is consuming a week. And if you break that up into particles, it's about 100,000 particles a year. So once again, there's an issue with international regulatory agencies trying to define what actual, if any, risk is associated with human consumption of this plastic material. So there's a recent survey done by the Accenture Chemical Global Consumer Sustainability Survey. And as I mentioned, These were over 6,000 consumers in 11 different countries. So there is a public driving the market for recycled plastics. And I think this is very important from having companies invest more and more time and money into recycling plastics. So essentially 83% of consumers believe it's important, and they expect to increase their purchase of plastic products, and this includes foods that are packaged in material which is being advertised as being recycled. So you can advance this to the So, and unfortunately, I think basically there's still some work that needs to be done, because only 37% of these consumers identified environmental concerns as being important. So it's sort of, you see the somewhat difficulty that's currently faced with recycling plastics, in that price is still important to the majority of the consumers, and the majority of also, at least that participated in the survey, didn't identify environmental concerns, which I think is the major driver internationally for trying to restrict the amount of plastic that gets into landfill or to aquatic environments. So we'll touch briefly on the recycling products. These are essentially what you see for the main types of recycling is either mechanical or chemical recycling. Mechanical cycling is simply when you take the waste plastics. These are all chewed up. Typically, they produce pellets. The pellets are specific to one different type of resin code. And then these are used to generate additional packaging material, whether it be for food or from the original products, or for other types of plastics. So typically, mechanical recycling is also referred to as primary recycling. So in certain cases, there is waste associated with the production of the primary plastic. This waste can be collected, shipped off to different suppliers who will use it in a mechanical recycling process to produce new plastic. So in this particular case, it's recycling of the waste, but it's recycling of plastics that have never been used. So the process to do this is quite a bit more simple than actually having a post-consumer type of plastic recycling, which tends to be what you see in chemical recycling. So the two major types of chemical recycling is depolymerization. And this is when you have starting chemical materials. These chemical materials are used to produce monomers. And typically these monomers are then used to produce the polymers. So the major polymers that are inherent in every type of packaging material or plastic material. So essentially in the depolymerization, the starting materials are typically broken down into the monomeric feedstocks and then used to produce the packaging material. So, and polyester and polystyrene tend to be examples of depolymerization of plastics. So another example is something like polyvinyl chloride. Typically, it can be broken down into vinyl chloride monomers, which are then polymerized into polyvinyl chloride. The most extensive type of plastic recycling is from the total pyrolysis. So essentially, if you think the monomeric units are then broken down into the initial starting material, and theoretically, that would then make it available to put into production of any type of plastic material. So typically this involves the use of high temperature, and the example of a short chain hydrocarbon chain, because once again, all packaging material has an environmental source of being from an oil-based feedstock. You can break plastic material down into naphtha. So this tends to be the most extensive type of recycling process because it can handle a wide variety of mixed-use plastics. So essentially, it doesn't have to be specific to a single type of plastic, such as the depolymerization process. It can handle all types of plastic, and knowing that it can be broken down into the starting chemical ingredients of the monomers. So essentially what we're looking at is these type of recycling processes all have inherent guidelines or standards that are currently being developed and applied to food packaging. Food packaging tends to be the more difficult process because typically you're not dealing with, in other types of processes, you're not dealing with the potential exposure to the chemicals themselves. So I think, and this isn't specific just to recycled plastics, but all plastics contain residual chemicals used in their manufactures. And these can be anywhere from the chemicals used to produce the monomers themselves, the polymers, but also a wide variety of chemicals that are added to the plastic monomers and polymers to increase the properties of the plastic in order to make it a better food packaging material or just a packaging material. Also, what we're now seeing is there's a large amount of chemicals that are being added specific to food packaging that have active functional properties. So you have antioxidants that are being added to the packaging material, and that's not just for the package itself, it's to have an antioxidant effect on the food that's being packaged with it. Another prime example is that you have antimicrobial substances that are being added to food packaging material. And typically what you see is these are being used to package meat, and it has an antimicrobial effect on the surface layer of the meat that contacts the packaging material. There's an estimate recently that there's up to 10,000 chemicals that are available for migration of plastics from plastics into food. And this really, there's a wide number of factors that go into determining how a food might be receptive of a migrant from packaging materials. So we can go to the next slide. So this is simply just an example that we together for agency where we've looked at the number of potential migrants. Each one of these red dots illustrates there's over 400 chemicals that have been assessed for migration from food packaging. So you see that, you know, the amount of potential migration of a chemical from packaging material runs almost 9 orders of magnitude, all the way up from milligrams per kilogram body weight per day to low femtograms per kilogram body weight per day. So there is defined processes where an estimation can be made based on the physical chemical properties of the packaging material chemical and the food uses itself in terms of estimating what the potential human exposure will be from the use of packaging material. So essentially, when we're dealing with recycled plastics, we have particular issues that are specific to recycled plastics and not to virgin plastics. So there have been a number of studies that have shown that when you compare recycled to virgin, and this is primarily polystyrene, HDPE, high density polyethylene, and polypropylene, that they typically show a higher volume of chemical migration than the virgin material or the new material. And this is likely related to some degradation of the plastic polymer and also the type of recycling processes that have been used. So not only do you have to consider the type of products that might be present in the package from its manufacturer, But for recycled plastics, one of the major issues is that there could be previous use, whether this is specific to food or has non-food applications, but more specifically, misuse of plastic packaging. So you find that people, when they, consumers, when they have an empty plastic material that has a good stability, has good resistance to a wide number of chemicals, tend to use this for non-food uses. And this particularly can be used for recycling plastics. So the issue would be is when you have a plastic that has undergone non-food use being put into a stream for recycled plastics for food use. The other issue is that there's generally a heat involved, and once again, the highest level of thermal type of plastic recycling associated with pyrolysis. You generally tend to see some sort of decomposition of material that you normally don't see when you're dealing with new plastic material. So you don't have this high heat used as part of the extruding or the formation process of the packaged material. So we can go to the next slide. And this, this simply is a graphic illustration of the type of chemicals that you could potentially see resulting from the use of recycled plastic. So typically when you're dealing with new plastics, you don't have breakdown products, you don't have contaminants. You'll have byproducts, oligomers. These could be both the polymers and the monomers, but you can also have additives and other factors that are included in the raw materials. But the major issue that you have to deal with when you're talking about recycled plastics for food use is contaminants. So unintentional use of non-food plastics, making it into a food stream, and breakdown products due to chemical and pyrolysis processes that could potentially form new or unique compounds. And we can go to the next slide. So this just simply illustrates that this is a study done by people in EPA recently. They looked at a small number of recycled food contact materials and compared it to the virgin materials. And following an extraction with dichloromethane, they did a simple identification using gas chromatography, mass spectroscopy. And you see that, especially on the left, a wide variety of chemicals were identified in the plastics for different categories. And the white material is unfortunately representative of the recycled plastic. So essentially, for most of these different types of chemical classes, you find a higher occurrence of these products occurring in the recycled plastics, the white, versus the new materials versus the blue. And one of the other issues you see, which is quite, I guess, does illustrate the issue with recycled plastics, is that typically for food use plastics, and this refers to the figure on the right, you generally don't see things such as fragrances, flavoring, and nutrients, but more specifically, flame retardants making it into food use plastics. So when you go through a recycling process, this probably illustrates that there is inclusion of non-food use plastics in the waste stream that's going into food use plastics. So you get these unknown chemicals that are more referred to as contaminants because they were never used primarily to in the food packaging material. So we can go to the next slide. And once again, this simply illustrates what you find. You'll see that the dark blue is post-consumer. This is low-density polyethylene, so films and bags, versus the high-density polyethylene, which is the lighter green. What you have here is these are plastic pellets that are collected from recycling facilities in Germany. And once again, it was an extraction to look at both volatile and semi-volatile chemicals that could be occurring from these. In this particular experiment, the screening, and this is done by, once again, gas chromatography, mass spectroscopy, which tends to be a typically used analytical procedure, identified over 1,000 tentative compounds that had been extracted from the plastics. And this simply is the next slide. What you have of these 1,000 different compounds, the majority tended to either be contaminants, and this is the high density polyethylene, or something associated with the polymer degradation. So a chemical that you would not normally see in new food material. Now, the good news is that when you identify over these 1,000 peaks, you can then compare them to similar spectral analysis, and mainly by the National Institute of Standards and Technology. They provide spectral libraries for a large number of chemicals, depending on what type of analysis is done. And the National Institute of Standards and Technology has spectral libraries for these type of chemicals, numbering over 300,000 chemicals. So typically what you find is there's the previous slide showed what resulted from the peak. Those spectral peaks can then be identified through the reference library and categorized into various areas such as this. But I think the main issue in terms of a takeaway is the fact that there are the majority of recycled plastics include a high component of contaminants that were likely never present in the new or starting material. So this slide simply illustrates, some of the issues that are specific to recycling plastics. So when a manufacturer attempts to set up a plastic recycling, especially for food use plastics, the regulatory agencies are asking for sufficient information on a large number of issues, primarily, how the plastic waste is collected, how you are controlling the source of plastic material into the waste stream. So this is a sorting process. Are you able to sort non-food use plastics from food use plastics? But I think the major issue that's specific to recycling plastics is that all the current processes rely on the use of chemical surrogates to create a worst case scenario for migration. And so essentially, instead of looking for specific migrations of chemicals from the plastic itself, you're looking that your washing and cleaning process is effective in removing the vast majority of chemicals that may be in that plastic from non-food use. So essentially, regulatory agencies have defined a number of different types of chemicals that are added to your washed and clean plastic waste prior to it being approved for food use. And in this particular case, the Food and Drug Administration in the US has identified a number of different solvents, and these are expected to cover the major chemical classes. So volatile, polar, nonpolar, metals, non-volatile, polar, and nonpolar. And simply, what they're saying is that the majority of non-food use plastics can be represented by likely chemicals specific to cleaning products, to solvents, to pesticides, and to some use of, say, an industrial motor oil type of process. So a heavyweight motor oil coming from a petroleum-based product. So all these chemicals are expected to show they're added at a particular, generally they're put into the plastic waste. They're kept there for approximately 2 weeks at 40 degrees Celsius. And then following that, there's a cleaning process. And then there's an attempt to analyze for all these chemical products to ensure that the cleaning and removal process has been sufficient. So, and typically what is used when you're looking at a migration is that any chemical that migrates into a food, whether this is from regular plastic or recycled plastic, and it's determined to be present at less than 0.5 parts per billion, would generally be considered to be a negligible risk. And this is a limit that's specifically been developed, and the process has international acceptance, and it's referred to as the threshold of toxicological concern. So essentially, the idea would be is that if that chemical migrates from the plastic material into the food, and it's at 0.5 parts per billion or less, the regulatory agency has reasonable assurance that that chemical does not represent a risk to human health. And this also goes with the use of these contaminant surrogates. I mean, they would have to, your cleaning process would have to show that you can effectively remove these contaminants down to 0.5 ppb to ensure that non-intentional use has been accounted for from a particular contaminant perspective. So generally, this 0.5 ppb, looking at a migration for food, that usually, depending on the type of plastic, results in about a concentration of 200 to 300 parts per billion in the material itself. So the migration factors following creation of the plastic material, 200 to 300 parts per billion, once again, depending on the type of chemical and food packaging material, would tend to result in less than the threshold amount of migration. So I won't get into a large amount of detail, but this is the basis for developing that threshold of toxicological concern. And once again, this is something that has been adopted by a number of international regulatory agencies. It's used not only for packaging material, but it's also used for the assessment of non-intentionally added substances or detected substances in therapeutic products, in human drugs. There's an application for it that's been ongoing for a number of years for flavoring ingredients that are used in food. All follow this category. And this stems from a concept that was developed over 50 years ago, that the toxicity of a chemical is directly related to its chemical structure. So initially, over 600 chemicals were assessed for their toxicity based on their chemical structure, and they fall, at least logarithmically, into these three categories. So the first class of chemicals is essentially the highest degree of toxicity, and there's been a number of chemical structures from this class of chemicals that were identified, and those are applied from a screening perspective of chemicals to ensure that they will not exceed this potential level. So there's a number of different good publications, including a consultation report that was produced by the European Food Safety Authority and the Joint Expert Committee on Food Additives to define and update this threshold of toxicological concern and how it's applied in chemical risk assessment processes. So, so essentially, what we're seeing is that the issue specific to recycled plastics is that in order to show you've effectively controlled for the input of material into your plastic recycling, you generally, if you approach an organization, a regulatory agency, to provide recycled plastics, you have to show that the initial collection and sorting material of material from post-consumer use to the fabrication of the product has been controlled. So is it a mixed waste stream, or is it a controlled waste stream where you've identified the particular codes for the plastic recycling, and more importantly, that you've been able to sort the plastic based on food use and non-food use. So, and I think importantly, if a manufacturer can demonstrate that they have sorted their products effectively and all plastics coming into their waste stream are only from food use, the previous surrogate migration studies can be amended. So these are primarily meant to identify potential contaminants that are entering into the feedstock source from non-food use of plastics. So just in summary, we can see that it's the primary driver for creation of a market for recycled plastics is the amount of waste being created, which has been created and continues to be created, and the inadvertent escaping of this plastic waste both from landfill into aquatic environments. So there's a number of countries, including Canada and the EU, who have already legislated restrictions on the use of type of single-use plastics, and by certain dates are encouraging sort of a circular economy. And the circular economy for food use plastics would be a food use plastic container that can be recycled is recycled only into food use. So the good news is that recycling processes tend to be rather consistent for plastics for food use. And there have been approved processes, the first one being for recycled polyethylene terephthalate. So there's defined processes that have been approved and marketed worldwide for the collection and recycling of polyethylene terephthalate, primarily bottles. And this is why this type of chemical resin usually has the greatest percentage of recycling for food use plastics. But there's also recycling processes for polypropylene and high density polyethylene that have been approved and are currently on the market. So, and once again, you're now seeing is that a lot of the plastic waste that has been accumulated and not recycled is driving the vision or the sort of the direction of various countries that the majority of plastics being placed on the market will either be reusable or recyclable. But essentially, I think what has to be recognized is that there are unique specific safety issues that have to be addressed through this risk assessment processes. And that starts really from the collection and sorting processes prior to actually generating a waste stream that can be used in food recycling plastics. And that is it. Once again, I thank you for your time and encourage any questions that you might have.
Thank you. Thank you very much, Mark, for this comprehensive presentation and also for giving us an overview of the levers of recycling, the potential for use of these materials in food contact application and in food packaging application in particular. I believe we have a few questions that were posed by colleagues online, and I believe one participant in particular actually asked a number of questions. So we thought maybe that we give you the floor. I believe it's Mohammed Altaf. So Mohammed, we're going to give you the floor. So you can please ask your questions directly to Dr. Mark Feely. Mohammed, if you don't mind, please raise your hand so that we can identify you and then give you the floor. I believe that is happening right now.
Right. Hello, Mr. Mark. Thank you so much. Professor Samuel, thank you so much for such a very interactive presentation. And I believe I worked this time today. And it's a countless, learning today. I have some questions. I hope Mr. Mark will read and reply. The question was, you have mentioned class 7 is rarely used in recycling, but we have observed in bottled water industry, PC bottles are mostly recycled. And what is your opinion worldwide, the recycling of PC bottles? And my second question was, you have mentioned that HDPE can be recycled 10 times. What is your opinion about other plastic materials? How many times they can be recycled? And the very important question with respect to food safety is how we can reuse these plastic bottles such as PC or PET bottles in different industries, especially in water industry. And my last question was, which is because from your presentation, each slide has very good information. You have mentioned that there are around more than 10,000 migrants from the plastic material to the food products. From where we can get this data so that when we will assess any packaging material, we can take a decision based on this available scientific data. And once again, trillions of thanks from me to you and Professor Samuel for such a very good lecture. Thank you so much.
Thank you very much, Mohammed. And Mark, if you don't mind taking these questions, I don't know if you're able to see the questions in the Q&A section of the Zoom, Mark. It is basically on the right-hand side. You see Q's and A's. Mohammed was kind enough to type the questions.
Yes. Well, thank you, Mohammed. All very good questions. I think your initial question about polycarbonate, you're absolutely correct. It does fall into the category 7. The good thing about polycarbonate is that it does have very good tensile properties, so it can be used for a number of uses. Typically, it has an upper temperature range, so you wouldn't use this for processes that are involved in high heat, but it's absolutely perfect for bottled water because it provides a good shatter resistance, and it can be reused on a number of occasions. Now, it tends to be, I think, the anomaly of a type of packaging material that was produced after, near the end of all the resin codes being developed back in the 1980s. So it's placed into that category 7, which tends to be other. So I think, if anything, it probably could stand to have its own recycling code in terms of a resin identification material, because the recycling tends to be difficult for polycarbonate, but the reusability is very high, especially if you can control the source. Because if you're simply generating a large, say 18 liter carboil polycarbonate bottle for drinking water, and you're collecting those, the recycling process for that is very minimal. All you have to do is demonstrate that the product itself has been effectively cleaned, and that's primarily from a microbiological perspective, and you can reuse that for bottled water. So, I think, as you've indicated, polycarbonate does fall into category 7, but one of the things is that the polycarbonate is somewhat difficult to totally recycle, and we're talking about either a thermal or pyrolysis recycling. But the reusability is very high because the resin material has a good tensile strength and it has a good shelf life. Unfortunately, polycarbonate also falls into that category of something with a very long environmental decomposition rate. So it's good that a lot of polycarbonate bottles are reused. So there's an issue between being recycled, which either breaking it down and producing new products, or being recycled from being reused, and from the latter, being recycled to be reused, polycarbonate is very high. So I think it's sort of they use this category 7 as a catch-all, but yes, you're quite right. Polycarbonate bottled water bottles can be reused in a number of cases until the tensile strength breaks down, and usually it's based on some physical obstruction of the polycarbonate bottle that results in its half-life determination. So your next question, I think, as we see here, it's about high-density polyethylene. High-density polyethylene has a higher tensile strength, therefore it's more malleable. It tends to have a higher temperature range usage than something such as polyethylene terephthalate, the the crinkly bottles. But once again, the polycarbonate, the large drinking bottles that are used for water, probably has at least, once again, we're talking about reusability versus recycling. A lot of the HDPE tends to be recycled either through a mechanical or a thermal or a pyrolysis product, where it's the feedstock is primarily HDPE, but the feedstock is not restricted to food use, because there's a lot of non-food use HDPE use that can still be recycled into food use. So in this particular case, whereas polycarbonate is specific to typically a bottled water product and can be reused, so cleaned and refilled at least 10 times, if not more, the HDPE tends to be recycled. So it actually goes through a restructuring process, and then it's extruded into different types of material, different sizes for different uses. If it happens to be food use, then you would have to control the waste stream coming from food use HDPE, not including non-food use.
Yeah. Mark, I'm looking at the time, and I know it's very early in Canada, but if you are okay to stay with us for the upcoming period, we may tackle the rest of the questions, including actually potential questions from other participants subsequent to the upcoming presentation, if that's acceptable to you.
Oh, totally, Samuel. I have no problem with continuing. It just, it's, as you might remember, it's very cold and icy in Canada these days, much more so than Dubai. So I'm indoors and not going outside.
Great. So we'll take advantage of that. Thank you so much.
Okay.
Well, then we'll continue, in fact, with the second part of this webinar. And now, after reviewing the conditions of assessment, some of the considerations to be looked at, we're going to be looking at aspects of regulatory management. And we have the privilege to have with us Dr. Dario Danelli. In fact, actually, Dr. Danelli is not with us in person, but provided us with a recording of his presentation. Dr. Danelli is a regulatory expert and managing director of Dario Danelli Policy and Regulatory Affairs. And we will have, in fact, through Dr. Danelli's presentation, an overview of conditions of regulatory management of recycled material, with, again, an emphasis on recycled plastics.
Good morning or good afternoon. My name is Dario Danelli, and I'd like to thank you, the organizer, for inviting me in this conference. Unfortunately, I will not be able to attend because at the time you are looking at this presentation, I will be in a flight. You have my email address, so any question you have or you might have after the speech, you can email to me. Let me share my screen. A minute. Okay, I hope you can see my screen now. The title of my presentation is about sustainability, and particularly for recycled plastics. So the point that I'd like to cover is how to ensure consumer safety while using plastic coming from recycling processes, and particularly for post-consumer recycling processes. I will try to answer some questions during this presentation. What kind of food safety and quality risks might be identified with recycling for polymers, in particular mechanical recycling, which is the most widespread process for polymer recycling, how this risk can be managed through legal mechanisms, and how these legal mechanisms are in place in different jurisdictions across the world. What kind of difference are between the approaches used in the United States and Europe concerning standards for safety assessment and protocols, and how are the recycling system validated by using these systems? But first and foremost, circular economy. So the transition towards a circular economy or a more sustainable economy has become a priority in many countries, certainly in North America and in Europe, but increasingly also in other countries in Asia, like in China and in Africa, Latin America, etc. So circular economy has now become the predominant business model in many fields: transportation, building, automotive, etc. Plastics have been subject of an important action plan known in Europe as the Plastic Strategy in 2018. This is a strategy which aims at transforming the way the plastic products are designed, are produced, used, and recycled in the European Union. Plastics are certainly an important material in our economy and in daily lives. However, they might have negative effects on the environment if they are not properly managed at the end of life, at the end of their service life. The plastic strategy aims at making recycling profitable for businesses through rules on packaging to improve recyclability and increase the demand for recycled plastics content, as well as improving separate collection, so curbside collection of plastic waste. Developed countries have adopted circular economy principle as a part of their growth strategies. And this model not only implies a lower impact on the environment and ultimately on environmental health, but also includes many other advantages: boosting recycling, preventing the loss of valuable materials, creating jobs, and also creating economic growth. Adopting new business models and building knowledge that might eventually be translated into other technology fields. Developing eco-design for food contact packaging materials, but not exclusively in this field, and promoting industrial symbiosis, for example, through integrated collection, sorting, recycling, and use systems. It is widely recognized that the consumption of resources of our planet, of course, cannot be indefinite, and that the economic growth that so far has been made possible with the intensive use of oil, mineral, water, forest, other resources that cannot be replaced is now close to downturn. And circularity in the economic growth is already a reality and will certainly become more and more important, a strong driver for the future economy. It is impressive how things have changed rapidly in the last decade, when public opinion's awareness has enormously increased towards environmental themes, and support to environmental activists has literally boomed. Organizations such as Greenpeace, WWF, the Ellen MacArthur Foundations, and other organizations now have a wide support and are often partnering with governmental organizations for the implementation of strong initiatives with very high impact on business and on the society at large. Many policies fostering circularity of plastics have been adopted on a global basis. For example, the European Union set challenging targets for plastics, 25% recycling for total plastics by 2025 and for 55% by 2030. and incorporation of recycled PET in beverage bottles of 25% by 2025 and 30% by 2030. In addition, it is requested to collect 77 of PET bottles by 2025 and 90% by 2029. It is obvious that such a high collection rate must correspond an equal increase in the capacity of the PET recycling or the plastic recycling in general using packaging materials. For example, for polyester, the current share of rPET over the total PET in Europe is about 1/3, and almost all of it used in packaging materials. This figure accounts for a shortage of rPET in the European market and, of course, a boosting of price. It is expected that the policy adopted will provide industry with increased capacity of rPET. In the US, the initiatives are more taken at the state level rather than federal level. However, there is an increased number of states, such as California and New Jersey, the Northeast Coalition, that have adopted measures that promote directly or indirectly recycling of plastics, and in particular PET bottles. Sustainability is a key word, and all these initiatives push the economy to become more sustainable, or in other words, to decouple the economic growth from the consumption of resources. There is no doubt that plastic recycling represents a highly sustainable industry. However, there are several challenges for presence of contaminants in the post-consumer plastic waste stream, which makes the post-consumer waste recycling more critical, particularly when using food contact application. There are main contaminants that originate from the packaged food itself, such as limonene from beverages, oils, fats, and aromas, which might be absorbed in the plastic. There are also incidental contamination for misuse, for example, storage of solvents or fuels or other liquids into the bottle. Some non-food contact containers might also be source of contaminants, lindane from shampoos, methyl salicylate from cosmetics and other solvents, and degradation products and additives. Degradation products typical from PET is acetaldehyde, but also you might have oligomers in all kinds of plastics, particularly polyolefins. There might be residues from chemicals used in the process, such as alkali from washing and removal of labels, and other plastics which might taint the stream that is to be recycled. For example, in the PET recycling, presence of PVC, polyolefins caps, and other components such as adhesive, they might be, and they are in fact detrimental to the quality of the stream. PET is certainly one of the best suited polymers for recycling. And this slide shows why PET is so best suited. It is not indeed the only one, but it is intrinsically shows physical chemical properties that allows easier and faster cleaning from any potential contaminants that might have polluted the bottle during the post-consumer phase. PET has a high melting temperature, over 250 degrees, which means that one can heat it up and volatiles are easily stripped, so that it can be found in the final recycled plastics. On the other hand, as its temperature raises to strip out volatiles, impurities and contaminants might decompose and might cause problems relative to spots, colors, and burns, and other kind of undesired contamination. That's why high purity is needed in the input stream, and the best the collection is, and the best is the quality of the final rPET. PT, unlike polyolefins, is produced via polycondensation. That means that it can be depolymerized by temperature and also by solvents, and subsequently it can be repolymerized. This leads to another form of recycling, which is not completely discussed into this presentation, which is chemical recycling, which is equally safe, mainly, but less frequent because of less economically sound. So the PT can be modulated in terms of molecular weight in the polymerization phase, giving enough time the polymer and the polymerization to proceed in the so-called solid phase polymerization, and this leads to an increase of the molecular weight, and then to better volatilization of the contaminants and possible decomposition products. The molecular weight is very important for processability. In fact, it is well known that for the PT bottles, the PT quality requires a high molecular weight than the grades used in other applications such as fabrics or textiles. The diffusion coefficient, which corresponds to the rate at which a certain molecule travels in the polymer matrix, can provide an explanation of the PT behavior. PT has a much lower diffusion coefficient compared to, for example, polyolefins. That means that the contamination takes place at a lower rate and will remain more superficial compared to other polymers. And this makes the decontaminations easier, especially this is true in dry condition, where the plasticization effects caused by moisture are reduced. When it comes to food contact material, the general safety requirements associated to food contact materials are reported in this slide, in particular in the top left. So packaging shall not endanger the consumer through product adulteration due to chemical migration from the packaging to the food, and shall not impart the taste on the taste and the smell of the product that is contained in it. The statement is taken from the European Regulation 1935/2004, which is setting the general requirements for all food contact materials. And in fact, with minimum differences, this statement is adopted virtually in all countries having regulations on food contact. For RPT, all existing regulatory systems aims at qualifying the suitability of processes to clean up the flakes and obtain food-grade PT pellets. These systems are focused on the process and not on the product, because the process shall be demonstrated suitable no matter the quality of the input material. Obviously, the quality of the input material is important, but within a certain range of contamination, the efficiency of the process in the removal of the contamination is what the regulatory agencies have interest in determining. A scheme for the core decontamination process is also reported here in the bottom of the slide, which is in fact very general but common to all decontamination technologies. You can see how the decontamination takes place in several different points on the line, in melt and also at the level of the production of the pellet. Now the question that you might have is, okay, but how do I prove that the process has the capability to clean up the chemical contamination, regardless of the chemical nature and the quantity of the substance that might have entered into the polymer, and no matter of their concentration? This is in fact the question that stands at the core of the overall decontamination process, and even more of the core of the application that recycling companies has to file to either the European Food Safety Agency or to FDA for the risk assessment of their process. The answer resides in the so-called challenge test, which is a test that demonstrates that the measures and to demonstrate and measure the cleaning ability of the process. The challenge test consists in spiky, clean virgin material with known amount of specific substances that are referred as surrogate contaminant in a quantity which is typically ranges between 500 to 1000 ppm. Then the process of the spiked materials are put into the process themselves, and one goes to analyze the level of spiked substances in the output material. This quantity in the output material determines the residue concentration. That is a function of the molecular weight and the volatility of the surrogate contaminants. And controlling this residue concentration will allow control and optimization of the process conditions. And finally, the level of these spiked substances shows the ability of the process to reduce contamination. And this is the parameter used by risk assessor to define restrictions, potential restrictions on the use of the material. So these surrogate contaminants are selected in order to simulate the behavior of any other contaminant, representing a range of volatility, polarity, and molecular weights. So the challenge test is not fully described in literature. There are several publications, but each laboratory adopts its own different procedures. In fact, the tests are very similar to the applications addressed to EFSA or of the FDA, although there are some differences. So, but the difference between the two systems, the European and the US, is not in the test itself, but rather in how the data are used by EFSA and by FDA to determine safety of the final polymer. So the difference stands on the third point, on how the different agencies use the outcomes of the challenge test to determine the process capability. But despite these differences, we can say that the level of safety determination achieved by these two agencies are practically the same. There are, as I said, two main systems for risk assessment and authorization of recycled plastics. The US and Europe, the European. US FDA approves recycling plants since 1991 and have approved now, well, 181 grades. There's probably a little bit more now. This has been done in 2021. The US system is conceived to address all kinds of plastics, although PET is the majority, but also includes polymers other than PET, such as high-density polyethylene and in some cases polystyrene. And for this reason, it can be considered a bit more flexible than the European system. The EU system is in principle also made for all plastics, but in practice, the way risk assessment is made by EFSA is applicable only to PET. And in fact, with very few exceptions, all these 240 recycling plants assessed by EFSA are 99% plants dealing with rPET. Well, we don't have a lot of time to go into the details of the risk assessment procedures, but if you are interested, you can email to me and we can discuss offline. So other systems in different jurisdictions are modeled after these two systems. Australia and New Zealand accept rPET authorized by EFSA or FDA. Mexico, the Mercosur countries have the same approach. And recently, Pakistan has adopted the same decision. Other systems, such as Canada and Japan, are equivalent to the FDA. And Thailand also is in the process of expanding its food control legislation and adopt a procedure using the same FDA approach. In the next slide, I show here the comparison between the American and the Ukrainian authorization system. Well, authorization is probably not the right word, certainly the assessment system. FDA issued a letter of no objection upon application of an applicant, of course. Whilst the European Union has a more complex legislation, which is going to change because a new draft for the legislation has been presented by the European Commission in December 2021. And in the European system, the European Food Safety Authority makes a risk assessment, and this risk assessment has to be adopted by the Commission and translated into a risk management action known as Commission decision. But these are only administrative details. Do not be misled by the fact that the US has a voluntary system. So the system in the US is voluntary, in fact. But in fact, even the FDA pre-market notifications for virgin polymers is not mandatory in FDA. To understand this, we should go into the legal construction of the US law, but as a takeaway message, you should notice that all operators who want to produce or use recycled plastics in the US actually go to FDA and obtain a letter of no objection. The EU system is more formal and might be more bureaucratic, requiring by law quality control and quality assurance, stipulating audits by the European national authorities of each member country, and requires a minimum purity of the collected PET stream of 95% food grade. So maximum of non-food grade, which must be contained into the input stream, should not exceed 5%. So the EU approach consists the general strategy of a regulation called 282/2008. This is pretty old. It's about 14 years ago. And as I said, this law is going to change. The new draft is being presented, and within 2022, the new draft will most likely be adopted. These systems enable direct food contact use of post-consumer plastics. The recycled plastics should comply with regulations for virgin food contact plastics, which is the regulation called 10/2011. Recycled plastics in the inner layer of the ABA structure are excluded from the legislation, although this is under discussion. It is not clear at this point in time whether this will last also in the new system. As I said, the process of recycling is subject to the EFSA opinion and the Commission authorization. So we have more than 200 opinions delivered, almost all related to PET. This slide it's a very, very short presentation of how EFSA approaches the risk assessment for recycled plastics. Actually, EFSA, the European Food Safety Agency, starts from a reference contamination level of flakes, which is considered a maximum of 3 milligrams per kilo PET. And this has been measured back in the 90s with a project which examined the contamination of several thousand of different bottles all across the different countries. So starting from this point, the EFSA, through the results of the challenge test, they can calculate the efficiency of the contamination. And through this number, which is the efficiency of the contamination, and using this formula, they came to a value which is called residue concentration, CRES, residue concentration. This residue concentration is then compared with a model concentration, which is calculated starting from the maximum tolerable intake of 0.025 micrograms per kilo body weight per day, which is corresponding to the concentration, maximum concentration for CMR substances. And by using this number and by applying migration modeling, they came to another number which is called model concentration. When the model concentration is lower than the residue concentration, then EFSA consider absence of safety concern. If not, if this is reversed, then there are safety concerns. As you can see here, the starting point is PT. So everything else which is different from PT would have problems of being assessed by EFSA because of lack of any system to calculate the residue concentration. Therefore, this system suits almost entirely to PT. I, of course, will not go into the detail here, but since no maximum concentration exists for other polymers such as HDPE, polypropylene, etc., then the calculation is not possible. And therefore, application which entails the usage of polyethylene, recycled polyethylene, they are either failing or just put on hold. This is, for example, the case of HD application received by EFSA in 2015 concerning, again, polyethylene, high-density polyethylene used in dairy product, milk product in the United Kingdom. So in 2015, EFSA received 2 applications from UK relative to the recycling of HDPE and for different uses. You see here, without getting into the details, let's say, deep was the analysis to select the field of application, the scope of application for this recycled polyethylene. However, the challenge test which was produced, it was executed. It was actually executed with conventional methods for PT in absence of other methods, which ended up into a concentration of the residue higher than the model concentration. And therefore, the conclusion from EFSA was that this method is unsuitable to determine safety. As a consequence, these 2 recycling processes for HDPE have been put on hold in 2015, and they are still on hold. The US approach, as I said, it's different, all right? As I said, it's voluntary. So US, unlike Europe, takes into consideration different type of recycling. The recycling of pre-consumer scraps, which is considered of no hazard, considered recycling anyway. So it is not master or not subject of letter of no objection. So pre-consumer scrap are easily and freely recycled. The so-called physical reprocessing, which corresponds to secondary recycling, called also secondary recycling, which is the one dealing with mechanical recycling, grinding, melting, reforming. And this is also has to be demonstrated as safe by means of a challenge test. Excuse me. And third is the chemical reprocessing or tertiary recycling, which is the regeneration of purified starting materials, also considered of no concern. So eventually, the system in place in the US is again dealing only the system of letter of no objection is only dealing with physical reprocessing or secondary recycling. FDA again approves the recycling process since a long time, and there is a system which is quite similar to the one in Europe. So recyclers and sensor, they have to submit an application describing the input material, the process of decontamination, result of the challenge test, and so on and so forth. And they have to demonstrate that the maximum concentration does not exceed the maximum acceptable level of contaminants. FDA issues a letter of no objection, and when anything happens in the technology, so if a different technology is put on the market, then you require a separate approval. And the new challenge test is to be is to be produced. So the main difference from Europe, as I said, is into the assessment system. Here, you have a starting point consisting on the maximum acceptable level of contaminants in the polymer, which corresponds to the estimated daily intake equal to 1.5 microns per person per day. It depends on the type of polymer itself. So the density, the thickness, and the quantity of this particular polymer which would be in contact with the daily diet. So here you have a calculation which is made by different polymers. What is changing is the density of the polymer, and what is changing is also the so-called consumption factors, or the fraction of any specific polymer which will enter in contact with the average daily diet. That means that there's nothing such as residue contamination here. So you only have a maximum residue which can be calculated by different polymers. So you see a maximum residue on polyester corresponding to 220 microns per kilo, of polystyrene of 300 microns per kilo, of polyolefins 320 microns per kilo, and of PVC. And in principle, you can make the same calculation for any type of polymers, which means that this system is much easier and much more easily applied to polymers different from polyester. For the US systems, there's nothing such as the 5% maximum contamination by non-food grade polymer. You can actually use both food grades and non-food grade feedstock, and the same standards of purity will apply. It would include also non-food in the feedstock, then the level of contamination in the challenge test, it is recommended to be increased. So to conclude my presentation, we can say that collected post-consumer plastics can be safely recycled into another food content use. The food grade RPT or are polyolefins or recycled polyolefins might be produced from validated decontamination processes, and the decontamination the validation is made through a challenge test based on a well-established principle of safety. The criteria adopted by US and Europe are different, but they are equally protective. And in principle, recycling process technologies that are accepted by the US FDA or by the European Food Safety Agency can also be accepted elsewhere. The opinions issued by FDA or EFSA can also be regarded as valid for compliance purposes. And the gap in the EU risk assessment process in general makes recycled polyolefins more difficult to be authorized, while the US FDA already includes assessment system, which is valid for both RPT and recycled polyolefins. As I said, the system in Europe is under revision. The discussion is there for quite a long time. So we are now close to a change, to a modification, and in a few months, we will be able to see how the new system will work. Hopefully, by opening the doors for quicker innovation and also making polymers other than polyester more easy to be accepted and utilized. And this is my last slide. Stop the presentation here. Thank you very much for your attention. I hope it was not too long. And again, if you have any questions, feel free to email anytime.
Our thanks go to Dr. Danieli for this great overview. In fact, actually, in organizing now this series of webinars, we have a realization there is a sheer amount of information and quite a bit of interest, just as we witnessed from the level of questions and interaction right now through the webinar. Unfortunately, we have gone beyond the time that was allotted to this webinar and to the webinar series overall. I guess one of the realizations as well is that we may end up needing to organize a panel discussion, bringing the various experts here and essentially enabling an interactive session with the participants. Please feel free essentially to provide us with your suggestions in this regard. In the meantime, we have noted the various questions that were posed, and we will attempt essentially to follow up with responses from the experts. I would like to also mention that we will be making available the presentations of the various sessions on the website of the Global Food Regulatory Science Society. In fact, using the same area in the website devoted to this event. So please visit the website later on and you will be able to find those presentations available. Now, I know that I've asked from Dr. Mark Feely to be with us still until the end of this webinar. Mark, do you have any final comments or contributions before we close this session?
Thank you, Samuel. No, I think I'm okay. I mean, as you've indicated, we're sort of at the end of the allotted time, so I think it's essentially a good idea that we can look at the questions that have been proposed and then try to prepare answers to send them out. And that would include if there is any specific reference material that people were interested in receiving. So, and once again, thank you for providing me the opportunity to participate in this very interesting webinar.
Well, thank you. Thank you, Mark. Thank you to all the speakers. And just to reiterate our appreciation to Professor Sandra Dominic, to Dr. Mark Feely, to Dr. Amin Assouf, to Dr. Scott Carrera, and to Dr. Dario Danelli. To all our participants, thank you for joining this webinar series. Please continue to monitor the website and we will advise you of upcoming events that we will be organizing as part of our knowledge dissemination series and capacity building initiatives. I would like to thank all the organizations, of course, that supported the organization of this event, the Global Food Regulatory Science Society, the International Union of Food Science and Technology, the Dubai Municipality, the Food Risk Analysis and Regulatory Excellence Platform of Université Laval. Also, a big thank you to my colleagues who made this event possible. You haven't seen them all. They have been working behind the scenes. So I would like to mention particularly Dr. Eli Bouyazbek, Dr. Amin Assouf, as well as Mohamed Salama for his contribution. Thank you all for your support. And we will be hopefully rejoining you in another event of this webinar series. Have a great afternoon, evening, morning, wherever you are around the world.
Thank you, Samuel. Goodbye.
Welcome to the first Capacity Building Event 2022 on the Food Contact Materials International Regulatory Framework and Food Contact Materials Recycling Regulations and Guidance. This event is organized by the Global Food Regulatory Science Society, G-Force,